right, so multiplying polynomials, you can see that up there. So let me get that on the screen so you can see it. There we go. All right, so we're going to be multiplying polynomials starting off. So this is a pretty straightforward section here. Nothing but, it says multiplying polynomials. That's what we're doing. So polynomials just means it's got more than one place where there's an x in it. And we're multiplying them together. What property is that? It's just distributive property. It's the same old distributive property we've been doing for years. It's nothing different. We're just calling it multiplying polynomials this time. So we're going to distribute 3x to both terms. So 3x times 4x would be 12. 3 times 4 is 12. X times x is x squared. And then 3x times 3 would be plus 9x. And you're done. It really is that easy. Okay. Add exponents when you multiply. That's the rule that we're using here since we're multiplying polynomials. Let's do negative 5x squared, parentheses, negative 2x minus 8. So a lot of negative signs there. Be careful on your signs. Negative times a negative turns into a positive every time. So be careful of that. So we're distributing negative 5x squared. So that'd be positive 10 x to the third power because there's a 1 on that one. So we're adding those together. And then negative 5 times negative 8 would be positive 40. And the x squared goes with us. And we're done. So just distributive property there. It's simple, easy stuff. Nothing too strenuous about that. When you get into problems like this, x plus 3 times x plus 4, some of you may in high school may have been taught FOIL method. Does anybody, does that ring a bell with you? You heard FOIL method? FOIL method is just another way of doing distributive property. It's just distributive property is all it is. You do the first term times the first term, and then the outer term times the outer term. I just do distributive property twice. That's all I don't ever call it FOIL when I'm teaching it. But it's the same thing. So x times x, x squared, x times 4, 4x. Then distribute the 3. Positive 3 times x is positive 3x. Positive 3 times 4 be positive 12. And then you're going to simplify the middle terms there are like terms because they're both just plain x's. So that'd be x squared plus 7x plus 12. That really is FOIL method. It's exactly the same thing, the distributed property in the same order. I just don't ever call it FOIL because FOIL only works when it's a binomial times a binomial. And so I just call it distributed property. So x minus 7 split times 2x plus 5, something like that. So mix in some sign changes there. So we're going to distribute x minus 7 to 2x plus 5. So I'm going to distribute positive x to both terms. It'll be 2x squared plus 5x. And then when I distribute this, I'm going to distribute negative 7. So be careful and carry your sign with you when you multiply. So that'd be negative 14x and negative 35. Just be careful on your signs. It's the most common mistake. Those two guys in the middle are like terms. You got 2x squared be minus 9x minus 35. So just distributed property twice when you got that going on. Makes for things working out pretty nice. Nothing too. And when you write your answers, notice how I've got them in order: highest exponent first, and then go down from there. Descending order is what what you want to have that in. So start with your biggest exponent on your letter and go down whatever letter is in the problem out of that. So let's look at kind of a special one. 2x plus 7 times 2x minus 7. Doesn't look any different than the last two I did. So I'm going to work it the same way. 2x times 2x would be 4x squared. 2x times negative 7 would be negative 14x. And then I'm going to distribute the positive 7. So that's a positive 14x. And that's a negative 49. What happens to the two middle terms? They cancel each other out. And there we have the final answer. Shortens up quite a bit there. Middle terms canceling out. Notice how the two factors that we're multiplying together are the exact same except for the opposite signs. That's going to happen every time that the factors look like that. They're the same, just opposite signs in the middle. So know that that's going to happen. Maybe you can take, see that enough. You can do the shortcut and get to the answer faster. Here's where the reason I don't do FOIL method is when I get to a problem like this, 2x minus 3 times x squared plus 7x minus 9. I used to teach FOIL method back when I first started teaching 13 years ago. FOIL method made sense to me, and I taught it, and it was in my textbook, so I thought it's important. But then I got to noticing after a couple of years that when students would get to a problem like this, they'd just stop, and they would only multiply 2x minus 3, and they would just forget this one and just do that problem because they ran out of things. Their FOIL method, they did all 4 of the things, the FOIL, and they didn't do the minus 9 that was there. And so I got to noticing that, and that's when I quit doing FOIL method and started just saying it's distributed property. You distribute it to everybody. So 2x goes to all 3 pieces there. So that's 2x cubed. And then 2x times positive 7 would be 14x squared. 2x times negative 9 would be negative 18x. Now here's my little trick to this. It's not much of a trick. It's just a way of organizing your thoughts. When I distribute the negative 3, I'm going to stack it up with its like term. So negative 3 times x squared is negative 3x squared. So I'm going to put that underneath the 14x squared. Instead of writing out this big long problem like that, it just, to me, makes it easier to put it together at the end. And then negative 3 times positive 7x would be negative 21x. And then negative 3 times negative 9 is positive 27. So I stack it up like that, and as the problems get longer, I just stack it up more. We'll do some that are a little bit longer than that in a little bit. And then I just put it together. I know I'm combining like terms. 2x cubed doesn't have anybody like it. 14x squared and a negative 3x squared would be 11x squared. That'd be 39x negative, and then the plus 27. You don't have to stack it up. If you do find writing it out long ways, that's absolutely fine. I don't care. Either way, I just trying to, I just like doing that because it helps me organize things a little bit better. Example G, x plus 5 squared. What does that even mean?
You do x plus 5
times itself. So you mean like x plus 5 times x plus 5, like that. That's what you mean. That's right. Absolutely. X plus 5 squared means it times itself. A lot of people make the mistake and they'll square x and square 5 and they say they're done. And that's almost right. You're just missing the middle piece when you do that. So the real correct way of thinking about that is saying, oh, it's x plus 5 times itself. And then just multiply it like we've been doing. So that'd be x squared plus 5x plus 5x plus 25. And the like terms in the middle there get us the final answer of x squared plus 10x plus 25. And you can guarantee that on the multiple choice quiz that they'll have x squared plus 10x plus 25 as an answer. And then they'll have this problem x squared plus 25 as an answer. And know that that is not right. Okay? Anytime you square something, write it out. It times itself. And then do the distributive property like we've been doing. Okay? It is too easy to make that mistake. So if we had 2x minus 3 squared, that means 2x minus 3 times 2x minus 3. 4x squared minus 6x minus 6x plus 9. Combine like terms. There are shortcuts to doing that. My wife and I were talking. She teaches math at another high school, and we were talking, and she asked me, do you ever teach your students the shortcut to that? And I told her, no, I don't, because it's not much of a shortcut, because you still got to memorize that the middle term is doubled. It's two negative 6x's there, so it's a double middle term. The shortcut is you square the front plus 2 times front times back. In this case, it's a negative 3 plus the back squared. And by the time I teach them how to do that, they could have just multiplied it out with the way they already knew how to do it. So I don't teach that shortcut. Some students pick up on it and they do it that way because they think they're faster at it, and that's fine. If you're doing it in your head, maybe it is faster. But for the most part, I don't think it makes it any quicker at all out of that. So don't worry about a shortcut on that. Let's do this one. I. X plus 2 to the third power. So instead of squared, it's to the third power. So what does that mean? Yeah, write down x plus 2 3 times. And then we're going to multiply that out. Now, here's how I go about doing that. I kind of block it off and say I'm going to do those two together first and multiply that out. So x times x is x squared plus 2x plus 2x plus 4. And then I'm going to simplify that. So that's going to be x squared plus 4x plus 4. And then I'm going to multiply that answer times the x plus 2. So x times x squared is x cubed plus 4x squared plus 4x. And then I'm multiplying 2 times x squared. That'll be 2x squared plus 8x plus 8. And combine your like terms there. You got x cubed, 6x squared, 12x, and 8. So cube something, write it out 3 times. Pick 2 of them to start with. I picked the 2 on the right. If you want to do the 2 on the left first, it doesn't matter. Just multiply them together. I've seen people try to just multiply it from this blue step here, try to multiply it all together at once. It never turns out well for most people. Very few folks do that well. So if you'll just take it one step at a time, you're going to be okay. This is not just crazy hard stuff. So multiplying polynomials, that's really what that first section is about. So we've actually already finished the first section of stuff. So we got 2 more to go. Pretty good. All right, so now the next section is going backwards from that. Factoring polynomials. Factoring polynomials is the inverse or the reverse of multiplying polynomials. So it's unmultiplying. You might want to think of it as maybe reverse distributive property sometimes. That's one way of that. So when you're doing factoring, I have this thing called, I call it the rules of factoring, and it can help us know kind of how to approach a problem and how to work with that. So the rules of factoring, the way that I teach it is the first thing you want to do is have the problem in descending order. That means like you start with x to the 4th power, and then you have x to the 3rd power, and then you have the x squareds, the plain x's, and then the plain numbers are always last. Okay, so make sure the problem is in that descending order first. That makes things a lot easier to do. It's not necessarily the only way to do it, but it does make the process a little bit more digestible when you come to do that. So descending order for the problem that you're trying to factor. The second thing you do before you do anything else is you look for a greatest common factor. And we usually abbreviate that GCF. Okay, a GCF is a number or set of variables that everybody in the problem has or is divisible by. So if everybody's an even number, we know that we could at least divide them all by 2. So that GCF might be a 2. Okay, so we're always looking for something that everybody's got to have it for the GCF to be part of the problem. So looking for a greatest common factor is the first type of factoring that you try to do. After you've done that, whether there was a GCF or not, you look at what's left, and then you count the terms. Terms separated by plus or minus, okay? Terms are separated by plus signs or minus signs, okay? Based on the number of terms, it tells you what strategy of factoring to use, okay? So when I was coming up in high school, I learned factoring by guess and check, and that was the way our teacher taught it, so that's the way we had to learn it, and that's the way we did it. And I was in college before I learned this way of doing it. And this is a little more systematic approach to it, and it's not so much mystery and smoke and mirrors kind of feeling. Because I remember in high school thinking, wow, this is magic. How does that work like that? And you end up getting decent at it because you practice it enough. But the systematic approach is a lot better. If there are 4 terms, we're going to use a method that we call grouping. And I'll teach you how to do that if you have never done that before. If there are 3 terms, we're going to use this thing I call the X method. And I'll teach you how to do that. No worries. And then if there are 2 terms, we could have a difference of squares, or it could be a sum of cubes, or a difference of cubes. And I'll teach you how to factor those as well, okay? So based on the number of terms that are in our problem, it tells us which methods to use out of that, okay? So 4 terms is grouping, 3 terms is going to be the X method, and I'll show you how to do that. And then 2 terms is going to be a difference of squares. If it's got squares on it, like x squared, that's when you know you're going to use that. Cubes is what exponent is cubed? 3. So that's how you kind of know which one of those it's going to be out of that. All right. So let's look at some examples, and we'll kind of try to build in all of these different ways of factoring in this section. So this one's a kind of hefty section here. A lot of stuff in it. Okay. So factor the polynomial. That's the instructions. Example A, 5x plus 10. All right. So first thing I want to do, that's a pretty small polynomial, really easy one actually, because it only has 2 terms in it, so it's not a whole lot of stuff going on. Is it in descending order? Yeah, we got the x in the front, the number in the back. That's the way it needs to be. Now, the first thing that I look for is a greatest common factor. What number goes into 5x and 10? 5. So the GCF will come out to the front, and then we'll open up a set of parentheses. What times this GCF of 5 would get us 5x? Just an x, yeah. What times 5 would get me this 10 right here? 2. We factored that polynomial. There's nothing left to do on the parentheses there because it doesn't have 3 terms to it. It's not got a squared on the x or anything that would allow us to even try anything. Okay, so GCF is all that one had. So GCF is what we're kind of practicing right here. Let's look at this one. 6x squared plus 8x. Is it in descending order? Yeah, we got x squared in the front, plain x behind it. So it's in the right order. Then we want to start looking at a GCF. What number would go into 6 that also goes into 8? 2. How many x's do they have in common? How many x's does this first term have? It's got 2 because it's x squared. How many does the second one have? 1. So the only number that they could have in common would be 1x. First one had 2, the second one had 1. You can only match up 1. So the GCF is going to have 1x on it. Now we need to open up parentheses and find out what's left. So we think, what times 2x gets me 6x squared? 3. And I need what else? Another x to make the x squared. And then what times 2x give me 8x plus 4. Okay. Greatest common factor is what we're using right now. And we'll add in the other stuff in just a little bit. Okay. Negative 15x squared plus 10x cubed. Is that in descending order?
No.
No, so let's put it in the right order. What goes first? 10x cubed minus 15x squared is the only other thing there is, so that's the right order now. Now, what do they have in common? What do 10 and 15 have in common? 5. How many x's do they have in common? 2. The first one has 3. The second one has 2. So you can only match up 2 of them. So that's why x squared is on the GCF. What's left in the parentheses? Two x minus 3. Good job. Three x squared plus 9x to the 4th. Is that in order? No, we need to rearrange it. 9x to the 4th plus 3x squared. Put the descending order on there. GCF of 9x to the 4th and 3x squared. 3 for the number. What about the x's? First one has how many x's? 4. The second one has 2. How many can you match up? 2 of them. So that's x squared would have to be on our GCF. Now we got to figure out what's left. What times 3 gets 9? 3. What times x squared gets you an x to the 4th? Another x squared. What times 3x squared gets me back 3x squared? 1. So I need a plus 1 there. When you pull out a GCF, ever how many terms were there to begin with? There need to be that many terms left in the parentheses. So there were 2 terms to begin with. We need 2 terms left in the parentheses. And that's as far as you can go with that one. Okay? Look at this one. A little bit different. Throw in a couple of variables here. And make it a little bit longer of a problem. 6x squared y plus 8xy plus 12y. Hard to do descending order on this one because you got 2 different letters to go by. But if you'll, a lot of times the best way of going about doing that is just go by the first letter in the alphabet. X comes first. So if we go descending order by x, it'd be x squared, x, and then no x's. So this one happens to be in what we'll claim as descending order. What do all of them have in common? 2 goes into 6, 2 goes into 8, and 2 goes into 12. Is that the biggest number that goes into all 3 of them? Yeah, okay, because 3 goes into it, and 6 also goes into it. Do 6 go into 8 or 12? Goes into 12, but not 8, so that messes that up. And then 8 and 12 have 4 in common, but 4 doesn't go into 6, so that throws that out. So 2 is the biggest number. What else do they have in common? Everybody has how many y's? 1 of them. So we'll pull 1 y out. Now the tough part, get what's left in the parentheses. What times 2y gets me 6x squared y? 3x squared. What times 2y would get me 8xy? 4x, good. And what about the 12y? Just a plain old 6. Factor that using GCF. Okay. All right, so seen several examples. GCF, that's the basic part of factoring. If you can't do GCF, we're going to struggle with everything else. So we got to be able to do GCF to be able to do any of the other methods. Okay, so let's look at a problem that requires one of the other methods. So example F. X to the 3rd power plus 6x squared plus 3x plus 18. Is this one in descending order? Yeah, got x cubed, x squared, plain x, no x's. Okay, so that's in descending order. All right, I look across the entire problem. Is there a number that all 4 terms have in common? 1. Will that help us any? Not really. Okay, it wouldn't change any of the numbers if we factored it out. So 1 is the only thing they all have in common. They don't all have an x on them, so we don't have a GCF on this one. So that brings us to that step in our rules of factoring where we're counting terms. Okay, this one has 4 terms, so we're going to use what's called grouping to do that. So with grouping, this is how grouping works. Okay, so I'm going to write over here grouping so that you know that this is the method that we're employing here. Grouping says you put it in descending order and then you group sets of 2. So I'm going to put these 2 together and then try to factor it using GCF. So what I'm doing is I'm just disregarding these these problems right now, and I'm just working on this part here, this half. What do x cubed and 6x squared have in common? How many x's? Yeah, the first one has 3 x's, the second one has 2 x's, so you can match up 2 of them. So that's going to be an x squared. What would it leave in the parentheses for that? What times x squared gets me x to the third? X. What times x squared gets me 6x squared? So plus 6. There's the first half factored. Let's factor the second half. So look at the positive 3x plus 18 separately. What would be the GCF of those two? 3. What kind of 3? That sign right there tells you to put a plus in front of that 3. What times 3, positive 3, would get me 3x? X. What times positive 3 would get me positive 18? Positive 6. What do we notice about those two sets of parentheses? They're both x plus 6's. They match. For things to be working correctly, they should match. If they don't match, things aren't working right. Okay? So what that does is allows us then to factor this piece further because they both have an x plus 6 in common. One factor is x plus 6. The other factor is this other stuff, x squared plus 3. And we factored by grouping. If we did the FOIL method or just double distributed property here and multiply all this back out, we'd end up back to the original problem. Okay, so anytime you want to check your factoring and see if it was right, you can multiply your answer back out and see if you got the original back. If you do, then you're probably right. Unless you didn't pull out the biggest common factor, you just pulled out a common factor. All right, let's look at another one of those. 4x to the third plus 2x squared minus 2x minus 1. Is it in descending order? Yeah. Is there a GCF amongst the entire problem? Almost, but that 1 on the end messes it up. It looks like 2 would be in common between everybody, but that 1 messed it up. So not 1. So then I count terms. 1, 2, 3, 4 terms. There are 4 terms. My rules of factoring tells me to use grouping to factor that. So I'm going to group first half together, second half together. First half, what do 4x cubed and 2x squared have in common? 2x squared. What's left in their parentheses? What times 2x squared gets me 4x cubed? Be a 2x. What times 2x squared gets me 2x squared? 1. So it's a plus 1 right there. Okay. Now, here's the tricky part. The second half has a minus 2x and a minus 1. What do those two have in common? A minus 1. They're both divisible by negative 1. They're both negative. So if we factor out a negative 1, what times negative 1 gets me negative 2x? Just 2x. What times negative 1 gets me negative 1? A positive 1. Now look at those parentheses. They match, don't they? If they don't, I got problems. But because they do, that means that things are working out good. Final answer, one factor is the matching parenthesis. The other factor, the stuff out in front of them. Okay. This grouping is going to be kind of useful when we do the next thing. So we got to make sure we're getting it. GCF is it's still the engine that makes everything go. We're still doing GCF. It's just mixed into this grouping step. Okay. Let's do another grouping problem. 25x plus 10x cubed minus 15 minus 6x squared. Oh gosh. What's wrong with this one? Not in the right order. So what should go first? 10x cubed. What's next? Minus 6x squared plus 25x minus 15. All right, so now we're back in the descending order that we need to be in. So that's going to make factoring easier to do. Not that it's impossible the other way, but it sure is a lot more complicated. Okay, now, is there a GCF across the entire problem? Not quite. Almost. The 6 messes it up. So how many terms are there? 4. So that tells me that I should be doing grouping. First 2, second 2. What do the first 2 have in common? 2 and what else? Good job. What's that leave in their parentheses? 5x and just a minus 3. We don't need an x because we got x squared outside, so that takes care of all the x's. What do these 2 have in common? Second half. 5? What kind of 5? Positive. That sign right there in the middle will always be the sign that carries down here. It never changes. It always is the same. Whatever sign is in the middle there is always going to carry down here. Okay? And then that leaves us 5x minus 3 in the parentheses. Hey, we did things right. Parentheses matched. What's my final factored form? The matching parenthesis. And then the other one is what? There you go. Boom. Questions about grouping? We're still going to use it some. I just want to see where we're at right now before we start adding the next thing in. Okay, so far we've dealt with GCF, and we talked about grouping, and that involved GCF, so that's part of it. Now the next thing we're going to look at is a problem like this. X squared plus 7x plus 12. Is that in descending order? Yeah, it's in the right order. Is there a GCF across the entire problem? No. Got x squared and x in the first 2, but the 12 messes that up. How many terms does that have? 3. So what does my rules of factoring say about 3 terms? X method. So I'm going to show you how to do the X method. You may have been taught something similar to this in high school. You may not have. I don't know. I don't know, depending on where you went to school and when you went to school, how they taught you to factor these things. The X method is just a way of organizing your thoughts. Okay? And I'm going to show you how to do this. So when you're dealing with a 3-termed problem to factor, you got this one on. A is the number that's in front of x squared. C is the number that's on the end. When you're doing the X method, you want to multiply A times C to get the top number that goes in this little area here. So we're saying 1 times 12. And that's going to be 12. And that goes in the top part of your X. The bottom part of your X is always going to be the B value, which is the number that's in front of plain X. What's B for our problem? 7. So there's going to be a 7 in the bottom half of the X. What our job is we need to find two numbers that multiply to be A times C and add to equal B. All right. So for us, we need two numbers that multiply to be 12 and add to be 7. That's what we're looking for here. Okay. So what it does is it narrows me down from every number in the world to only the numbers that multiply to be 12. So we think about numbers that multiply to be 12, 1 times 12. But if I add those two together, I get 13. So we know it's not those two. Then if I do 2 times 6, 2 times 6 multiplies to be 12. Well, what's 2 plus 6? 8. Really close, but not the right ones. What's the other option for multiplying to be 12? 3 times 4. So if I do 3 and 4, 3 times 4 is 12. What's 3 plus 4? 7. It's the right number. Okay. So here's what that does for us. It allows us to take this problem and turn it into a grouping problem. Okay. Instead of writing 7x, I'm going to put 3x plus 4x. This problem up here is equivalent to this one that I've written in blue. If I simplify this blue, it goes back to the original. It's the same problem. We're just manipulating it and making it look like something different. Okay? So what we can do now is take this problem and do grouping with it. Because we now have how many terms in the blue problem? 4. It makes it a grouping problem. I can group the first two together and the second two together. What's the GCF of x squared and 3x? X. That leaves us x plus 3. What's the GCF of 4x and 12? 4 goes into itself, and then it goes into 12 the 3 times that we need. Notice the parentheses. They match up. That's the right thing. That's what we want to happen. So our factors are then x plus 3 and x plus 4. Okay. On this step right here, it doesn't matter what order you put those two in there. If you put 4x first and then 3x, at the end of the problem, it's still going to be the same two factors. It'll just kind of look different in between. Okay? So you can do 3x and 4x, or you can do 4x and 3x. It doesn't matter in the middle. You're going to work out the same at the end. Let's look at another one. Yes, ma'am. Okay. Because 3 times 4 multiplies to be this 12 that's up here in the top, and 3 plus 4 adds to be this 7 that's in the bottom. So the numbers have to multiply to be the top, add to be the bottom. Multiply to be the top, add to be the bottom. Let's look at another one. 4x squared minus 11x plus 6. Is there a GCF? No. So I can go ahead and go to the X method. What number goes in the top of the x this time? A times C. 4 times 6 would be 24. So 4 times 6 says where I'm getting this 24. Okay. What goes in the bottom of the x? Negative 11. That sign needs to go with it. Okay. So we need two numbers that multiply to be positive 24 and add to be negative 11. So let's think about the things that multiply to be 24. 1 and 24. Is there any way that that's going to make 11? No. Okay. So let's keep going. 2 times 12. That's closer. If I did negative 2 and negative 12, and that multiplies to be positive 24, but that adds to be negative 14, which is close, but not the right ones. Okay. So 2 and 12 doesn't work. 4 and 6. Negative 4 times negative 6 is positive 24. Negative 4 plus negative 6, negative 10. So that doesn't, that's close, even closer, but still not the right one. What's the other option for multiplying to be 24? Negative 3 and negative 8. That's your other option for multiplying to be positive 24 and adding to be a negative. I know that both of them have to be negative because I'm multiplying to be a positive and adding to be negative. If I'm multiplying to be positive and adding to be positive, I know both of them have to be positive. Okay, so that's how I know that that's happening. Now, let's put them together. Which one would the 8 be most likely easier to do the GCF with, the 4 or the 6? The 4. So I'm going to write this problem 4x squared minus 8x minus 3x plus 6. Because to me, it makes sense to put the 4 and the 8 together and to put the 3 and the 6 together. The GCFs are easier. In my brain, they are. They're not really hard the other way, but it just makes more sense to me. Then we're going to group first two together. What's the GCF of the first two? 4 and what else? X. What's that leave in the parentheses? X minus how much? 2, because 2 times 4 would give me 8. All right. Second half. What do they have in common? What kind of 3 do I need to pull out? Negative. Remember that sign right there that's got the arrow pointing at it? That's the one that's going to come down here. So that's going to be a negative 3. And then what times negative 3 gets me negative 3x? X. What times negative 3 would get me positive 6? Negative 2. All right. Now look at our parentheses. They're matching. Factors are x minus 2, 4x minus 3. Okay. 6x squared minus 7x minus 5. It's in the right order. Is there a GCF? Nope. So I can go to the X method because there's 3 terms. What goes up top? Negative 35. 6 times negative 5. or negative 30. Sorry, not negative 35. I was reading the 5 and said negative 30. Okay? And then what goes on the bottom? Negative 7. So if we're going to multiply to be a negative, what do we know about the two numbers? Are both of them negative? No, one's negative, one's positive. So we know that. Now, because it's adding to be a negative, which one will be negative, the big number or the smaller number? They're going to add up to be negative. The bigger one will have this sign. Whatever sign is down here, if there's a negative up top, the bigger one will have the sign that's in the bottom. So we need to think numbers that multiply to be 30, and then we'll fix signs after that. 6 and 5. So negative 6 plus positive 5 is negative 1. That's not good. 2 and 15. Negative 15 plus positive 2 is negative 13. Still no good. What else? That's where knowing your multiplication tables is pretty helpful. Negative 10 and 3. And I tell my high school kids, if you don't know your multiplication tables, run to the Dollar Tree and get you one of them set of flashcards and just read through them every day, twice a day, and you'll know them within a week. Your brain can't help but memorize some things. So negative 10 and 3. So I'm going to replace the negative 7x in the middle with the 10x, a negative 10x, and a positive 3x. Which one do you want to put first? The 3. I think that it makes sense. I always think about that a little bit because to me it makes sense to put the 3 with the 6 because the GCF's easy. Mathematically, it doesn't matter which one you put first. You're still going to do GCF. You'll end up with the same final answer. Your middle step will look a little different from your neighbors, but it still works. Okay. So once we put those in there, we group first two together, second two together, GCF of the first two. (3x). What's that leave in the parentheses? Good job. Second set. What kind of 5? Negative 5. And then that leaves the 2x plus 1 in parentheses. And our factors are 3x minus 5, 2x plus 1. No, it doesn't. If you put 2x plus 1 in the front and 3x minus 5 in the back, it doesn't matter. Doesn't matter at all. Questions about that so far? All right, I want to show you a little shortcut for some of the trinomials or three-termed things that come up. What's different about this one compared to the last one as far as the original problem? Compared this example compared with the last the last two problems. There's nothing in front of the x squared, okay? That's the difference, okay? And we're still going to do the x method the same way. 1 times negative 14 is negative 14, and we want it to add to be 5. We're still going to set up the x and do the x method the same way, but I want to show you is a shortcut for when there's nothing in front of the x squared. What numbers multiply to be negative 14 and add to be positive 5? 14 doesn't have a lot of options. 1 and 14 and 2 and 7. 7 and negative 2. Here's the shortcut that can happen. Because there's nothing in front of x squared, you can go straight to the factors and do x minus 2, x plus 7. I do x minus 2 because it's a negative 2. I do x plus 7 because it's a positive 7. You can only do that if there's nothing in front of x squared. If you'll look back at example I, the one we started with x method, look at our x method. We had 3 and 4. Look at our final answer. Plus 3 plus 4. That only works if there's nothing in front of the x squared. It's got to be a 1 in front of x squared for that to work. So with that little shortcut, that can speed up things a little bit. If you don't like using shortcuts, that's fine. You don't have to. You can do grouping every single time. If I had x squared, let's do minus 36. Like that. Multiply to be 35, add to be negative 36. What does that? Negative 35 and negative 1, right? Because there's a 1 in front of x squared, I can go x minus 1, x minus 35, and I'm done. If there's a number in front of x squared, I have to do the grouping to make it work out. If there's not a number in front of x squared, I can go that shortcut. Just get my x set up, and then the numbers drop straight into the factors. Okay. If you like doing the grouping thing, it's probably not much quicker doing this shortcut, especially if you don't, if you're not comfortable with it. But it can speed things up as we move forward after this next test. Okay. All right. So X method, we've done GCF, we've done grouping, we've done X method, which led to grouping and GCF. And now the next thing would be if there are two terms. Okay. So let's look at if there are two terms. Example N. Let's look at x squared minus 4. Real basic. There are two terms. It's in descending order. There's not a GCF between x squared and minus 4. So we've checked all those boxes, and we saw that there's two terms. And in mathematics, a difference is what kind of problem? Subtraction problem, right? So there has to be a minus sign in it for this to work. Okay. This is a difference of squares because it has x squared. And what do we know about 4? What kind of number is it? It's even, but it's also a square number. Why is 4 a square number? Because 2 times 2 is 4. So 2 squared is 4. X squared is x squared. I've rewritten this as a difference of squares. X squared minus, that's the difference part, 2 squared. If I can rewrite it like that, that makes the factoring quick and easy. Okay? The trick is, or the shortcut is, that if you could rewrite it like this, then you're going to have two factors. Both will have x in the front. Both will have 2 in the back. One will be a plus, one will be a minus. And you're done. Now remember in the first section we were doing that multiplying out, and we had the same factors, just one had a plus and one had a minus. Remember the middle term canceled out? That's what this is. It's differences of squares. We had, let's do this one, 16x squared minus 49. I'm going to try to write it as a difference of squares because I think it's a square difference of squares because it has two terms. It's got x squared in it. And then what do I know about 16? What squared gets me 16? 4 and x being squared. You get 4x there. What square gives me 49? 7. That is a difference of squares. So my factors are going to have 4x in the front, 7 in the back. One's plus, one's a minus. try this one. 25x squared minus 144. What squared is 25? 5. What squared is 144? 12. 2 factors. 5x, 12, 5x, 12. One's plus, one's minus. It doesn't matter. It's just like the others. It didn't really matter what order you put those in. I just do the plus first out of habit. I don't know. There's really not a reason for it. I just do it out of habit because that's the way I've always done it, I guess. So really, really quick and easy way if it's a difference of squares. Where you've got to run into some trouble sometimes is if they throw this at you and they'll do something like this: 9x squared minus 26. And that looks a lot like a difference of squares. But it's not, because I can't rewrite it. Because 26 is not a square number. This doesn't work. So you can't do that. You can't factor it. This is, we'll call this prime. It can't be factored. Because 26 is not a square number. So that doesn't work that way. It has to be a minus sign in the middle, and you have to be able to rewrite it as the difference of two squares to be able to shortcut to the factors like that. Okay. All right. Also in that two-termed little part of the rules of factoring was the sum of cubes. The sum of cubes is similar to the difference of squares. Oops. It's more of a memorized pattern though. Okay, so you've got to memorize a little pattern here. When you have two things that are added together that are cubes, the factoring has a short factor and a long factor. The short factor is always the same as what you've got written here. So it's going to be x plus y. The long factor has the opposite sign in the middle. So it's a minus sign in the middle, a plus sign on the end. So the first term in the long factor, I used one of the x's. That means there are two left over, so that's x squared. The last term, I used one of the y's, so that's there's two of those left over. The middle piece is you multiply them together, x times y. Let's look at an example of that. Let's say we had x to the third power plus 8. And this is one of those things where you just got to memorize some numbers. You know that 8 is 2 times 2 times 2. That's how I know that that's a cube. And they don't get real big with their numbers on the differences or sums of cubes, because if you cube the number 4, you get 64. If you cube the number 5, you get 125. If you cube the number 6, you're getting a even larger number. The numbers get big really fast when you cube things. Okay, so they don't get to very large numbers. So you don't have to memorize too many of them. So now I've rewritten it as a sum of cubes. So I've got a long factor and a short factor. The short factor is going to have the x and the 2 in it. X plus 2. Just like that. The long factor, you're going to have x squared minus x times 2, which is 2x, and then plus 2 squared. But we know 2 squared is what? It's 4, right? That's the factored form. That's as far as you can go. That long factor will never factor any further. If it's a sum or a difference of cubes, the long factor will never go any further. difference of cubes. Got something cubed minus something cubed. Short factor, long factor. The short factor is always the same, x minus y. The long factor has the opposite sign in the middle. So it's going to be x squared plus xy plus y squared. So let's take a different cubic number. Let's say something like x cubed minus 27. 27 is 3 to the third power. So I know that that's a difference of cubes. So I got a short factor, be x minus 3. The long factor, be x squared plus 3x plus 3 squared. There's the final answer for that one. Sums and differences of cubes really is a memorized type thing. You memorize that pattern and kind of throw it in there. Let's look at another one and see if we can figure it out. 64 x to the third plus 125. When I look at that, I see two terms with a plus sign in it, and the x has a third power. That's how I know to even try sum of cubes. Okay, because that I see the x cubed and I see the plus sign in the middle. So I'm going to try to rewrite it as a sum of cubes. 64, 4 times 4 times 4. 125, I think is 5 times 5 times 5. And it is. So I have 4x and 5. This one's a little tougher when you get to the long factor, because I have to square 4x. And then I have to take 4x times 5 for the middle piece. And then I've got to square 5 for the last part. This one's a little tougher because of the extra numbers that are in there. But then all I have to do is simplify that. So that's 4x plus 5. What's 4x squared? 16x squared. 4x times 5 would be minus 20x. And 5 squared is 25. So we have a different sum of cubes there to work. We'll see as an example out of that. All right, I'm going to put some problems up here. We're going to kind of just try to look at them and use everything that we know about factoring. And I'm not going to say this is a certain kind, because we've kind of compartmentalized it as we've learned it. Now we got to start just, what if they mix it together? Because that's what's going to be like on the test. It's just going to be mixed together. So let's kind of mix it together. 10x squared minus 80x plus 160. So this is where the rules of factoring becomes very important, that you go down through those systematically through the polynomials to try to break them down. Okay, so first thing we want to check for is what? Descending order. Is that in the right order? Okay, check. Second thing. All right, 10 goes in all of those, so there's a GCF of a 10 for the whole problem. So let's get that out first. So we're going to pull out a 10. That leaves us x squared minus 8x plus 16. All right, so this 10 is out. We don't really have to deal with it anymore. It's just hanging out, watching what's happening. Now I'm looking at this stuff inside the parentheses. What does it have? How many terms? 3. So that tells me to try what method? X method. What goes in the top of the X? 16. 1. The 10, remember the 10 is just kind of, it's hanging out. We're not using it anymore. So there's a 1 in front of X squared. 1 times 16 is 16. What goes in the bottom of the X? -8. So we need two numbers that multiply to be positive 16 and add to be -8. -4 and -4. Can I use a shortcut on that part? Yeah, I can. The 10, remember the 10 is outside. It's not really part of the problem anymore. There's nothing in front of this X squared. So I can take that shortcut and have my factors X minus 4 and X minus 4. So that shortcut really is going to help me here to make this problem much shorter than it would have been. And then the 10 that was already out there is still there. How else could I write that? I could write it that way. Both ways are correct. X minus 4 times X minus 4, same thing as X minus 4 squared out of that. Okay? Let's see. Five X squared minus 20. Descending order? Yes. GCF. 5. So we can pull a 5 out. X squared minus 4. Hey, I've seen that before. I'm thinking that's a difference of squares because it's a 2 terms with a minus sign in the middle. The X has a squared on it. That's why I'm thinking that. And then that'll be X. And what squared is 4? 2. So my factors for that part are X in the front, 2 in the back, plus and minus. What else goes in my final answer? That 5 that I pulled out at the beginning, can't leave it off. It's still there. X to the third minus 5X squared minus 4X plus 20. One last problem. Then we'll get into the square root stuff. I think it's easier than this is. Is there a GCF? Is it in descending order? I forgot that part. Is it in the right order? Yeah, all right. So GCF, no. What method do we use to try to factor this one? Grouping, because it has how many terms? 4. X squared, the X minus 5, -4, X minus 5. So of X minus 5 and X squared minus 4. Now this one has got a little special part to it because what do we know about this from the previous example? This factor a little further too, right? This is kind of where we're headed with this stuff. That you can factor this piece as a difference of squares. So you get X minus 5, X plus 2, X minus 2. And now you factored a polynomial all the way. So that was a little special, and you just had something extra you could do at the end. That won't happen all the time. Actually, pretty rare that it does. But keep in mind, you might want to look for that if you factor something and that answer is not there, look to see if you might could factor it one of those pieces a little further. That can happen. Okay. All right. So let's do some square roots. So we're going back to that review chapter, which usually means the stuff's not too difficult, just a skill type thing. So square roots, you'll hear me say radicals a lot. Doing this, so I'll say square root all the time. I'll say radical. That's the same thing. Okay, they are exactly the same thing. Instructions will be simplify. So we're going to just simplify radicals. Is what we're going to simplify square roots. The square root of 9. Everybody knows the answer to that. It's what? 3. But why? Because 3 times 3 is 9. So it takes 2 3s to make a 9, right? That's what we're playing off of. Everybody knows the square root of 16 is 4. Where we run into problems is the square root of 18. I know we all could go to our calculator and we could type in square root. So hit second, the x squared button, and type in 18 and get the decimal for that. But that's not what we want here. We want to be able to simplify it and have an exact solution, because at some point this has got to be rounded. And we want an exact solution out of this. So what we're going to do, in the way that I teach simplifying square roots or radicals, is a factor tree method. Y'all remember in elementary school taking a number and making a factor tree for it? What numbers multiply to be 18? I think 6 and 3. That's the first one I think of. If you pick 9 and 2, that's absolutely fine. It doesn't matter as long as these two numbers multiply to be the one above it. Okay? Then I look at those numbers and say, okay, which one of those is not prime? Does it need to be a prime number? Yeah, it can only go into itself, nothing else will go into it. So which one of those is prime? 6 or 3? That means 6 will break down. 1 will go in 6. 2 and 3. Now here's what we're doing. We're taking square roots. So square roots, it takes 2 of them, right? To get the 9, it took 2 3s. To get 16, it took 2 4s. Look at this. There's a pair of 3s, right? When you're looking at simplifying radicals and you use the factor tree method, you're looking at the ends of the branches on your factor tree. 3, 3, and 2. There's a pair of 3s. We're looking for sets of 2s to do the square roots. Okay? So there's a set of 3s. So what that means is a 3 is going to come on the outside, and then that 2 is going to be left on the inside. 3 radical 2. And if I want to verify that with the calculator, I can hit 3 square root of 2, and I'm going to get the exact same decimal as the square root of 18 was. So I'm verifying that that's the right thing there, okay? Any pair that I find, I'm going to bring one representative from that pair outside, okay? One representative from each pair goes to the outside, okay? Square root of 24. If it was square root of 25, we know the answer. It's 5. But square root of 24 is not a perfect square number. So we want to break it down. And it doesn't matter what two numbers you start with as long as they multiply to be 24. So if you did 6 and 4, that's absolutely fine. If you used 8 and 3, that's fine. If you use 2 and 12, that's fine. It doesn't matter which ones you start with, just as long as they multiply to be the number above it. Are either of those prime? No, 6 I know isn't. We just did that problem. So that'd be 3 and 2. What do we know about 4? It's 2 times 2. Now, everybody at the end of the branch is a prime number. We're only looking at the ends of the branches. This 6 and the 4, they're not part of the problem anymore. The 24 is not the problem anymore. We're looking for pairs. So a pair of 2s right there. So that means a 2 is going to come to the outside. This guy and this guy don't have a buddy. They got to go back inside of the radical. And they're going to multiply back together to get 6. Anything that doesn't have a partner, doesn't have a pair, is going to go back inside and multiply back together. Pairs, sets of 2, one representative comes out. Anybody that doesn't have a partner goes back in and remultiplies together. Okay. Let's go to a bigger number like 108. Get more stuff out of that. Okay. 108. What do we know about 108? What numbers go into it? It's even.
3 and 36.
3 and 36. We'll do that. 3's prime, so I know I got to break down 36. What numbers multiply to be 36? 4 and 9. 6 and 6 would have done it too. 4 breaks down to 2 and 2. 9 breaks down to 3 and 3. Look for pairs. I got one pair of 2s. I got one pair of 3s. So a 2 on the outside, a 3 on the outside. What's left on the inside of the radical? That guy. He doesn't have a partner. We're going to multiply together on the outside. 2 times 3 is 6. Square root of 3. One of my fellow teachers, he teaches this a little different way. He asks his students to memorize all the square numbers and then divide by them. I don't know many people that can look at 108 just glancing at it and know that 36 goes into it. And it's the biggest square number that goes into it. I don't like doing it that way just because you've got to know even more about every number. And I think just knowing, hey, I just got to break the number down somehow. I don't have to break it down with a square number. I just got to break it down somehow. It makes it easier to me. Let's look at this one. Square root of 300. And let's put a negative sign on the outside to begin with. Okay? All that negative sign that's out there does is just waits to see what happens. It really doesn't affect how we do the problem. It just waits to see what happens. So we're going to break down the 300. How about 3 times 100? It's an easy way to get 300, right? And then break down the 100. 25 and 4. 5 and 5. 2 and 2. So I have a pair of 5s. Got a pair of 2s. So that's going to be the negative. Technically, what number is that out there in the front? It's a negative 1, right? And then a 5 and a 2. And then the 3 left inside. So that's going to be negative 10 radical 3. Let's say we had a 5 radical 48. So the 5 is already out there. And then they got a 48 underneath there. We're going to break down the 48. 12 and 4. 12 would be 6 and 2. 3 and 2. 4 is 2 and 2. 2 pairs of 2s. So the 5 that was already there. And then how many 2s come out? 2 2s. and then the 3 left on the inside. So it's going to be 5 times 2 times 2, which is 20. Radical 3. So if there's a number that's already out there, once you simplify, bring those out and multiply it all together. Okay. Not too strenuous. What if there's a fraction in there? We know the square root of 16? We know the square root of 25? That's really all it is. You just split it apart. Take the square root of the top, square root of the bottom. It really doesn't get any harder than that. We're not going to be too crazy on you as far as the fractions that we do. Let it around. Square root of 144 over 49. Split it apart. It's the square root of 144. Square root of 49. So, really is that simple. Okay? Square root of 6 times the square root of 12. All right, here's where we got to know a little knowledge about multiplying square roots together. The rules for multiplying square roots together is inside times inside, outside times outside. Simplify last. Okay? There's nothing on the outside of these. We could simplify first, but if we do that, we may end up having to simplify again at the end. So I always just say simplify at the end when you're multiplying square roots. So I'm going to multiply these together. So square root of 6 times 12, which would be square root of 72. And then I'm going to simplify that answer. 72. I got it from 6 times 12, so I'm going to break those down. 3 and 4. So there's a pair of 2's. And then a pair of 3's. That's going to be 3 times 2, square root of 2, 6 rather. Again, anybody, the 6, the 12, and the 4 are not part of the problem anymore because they're not prime numbers. I'm only looking at prime numbers at the ends of the branches. That's the only numbers that you're looking at from your factor tree. Okay. Let's say we had something like 3 radical 10 times 4 radical 18. Remember the rules. Inside times inside, outside times outside. 3 times 4 on the outside, 10 times 18 on the inside. So that's going to be 12 square root of 180. And I'm going to break down the 180. Started with 10 and 18, so I'm going to go back to that. 5 and 2, 2 and 9, 3 and 3. I'm just breaking down that number with the factor tree. 180 came from 10 times 18, so that's 5 times 2. 18, I did 2 times 9. If you did 6 times 3, it's 9. Same thing. And then I broke down the 9 again for 3 and 3. So I have a pair of 3's and a pair of 2's. A pair of 3's, pair of 2's. The 5 doesn't have a partner, so it stays on the inside. The 12 that was already there times the 2 times 3. So 24, or 12 times 6, 72, square root of 5. Inside times inside, outside times outside, simplify last. It really is that easy, okay? So those are regular square roots that we're dealing with there. let's talk about complex numbers, and then we're out of here. It's the last thing of the night. This is chapter 1, section 3, complex numbers. Complex numbers are the imaginary numbers that you've heard of before, okay? The definition, and something you need to memorize, is this little chart. I comes from the square root of -1. I squared is equal to -1. I to the third is equal to -I. And I to the fourth is equal to +1. Somewhere in your brain, lock that little chart in. You need to know it, okay? And be able to work with that. All right, when you deal with complex numbers, there's real parts, there's imaginary parts. Okay, the real parts, the number in the front. The imaginary parts has the I. Okay, when you the whole name imaginary numbers is quite an unfortunate naming accident in math history. There was a couple of guys that were both professors, and they were trying to challenge each other to see who could solve the toughest problems. This is back before no TV, no Twitter, no Snapchat, none of that stuff going on. So they were pretty bored, so they were pen paling each other, writing letters back and forth, and they would send a problem and say, "Can you solve this?" And that guy would solve the problem and send his buddy a harder problem and say, "Can you solve that one?" And they ended up figuring out that when you solve certain kinds of problems, you knew that there should be a certain number of answers. And at that time in history, they didn't have all of the algebra skills that we have now. It was still in development. People were learning how to do these different kinds of problems. And they would do these equations, and they knew that there should be maybe 4 answers to it. They could only find 2 of them, and they'd say, "I don't know how to find the other 2, but I know there should be 4, so there are 2 imaginary answers," and that's what they called them. And they kept calling them that, and they started calling them that to their students that they had that they're teaching at their schools. And the name caught on, and it just stayed that way. And over the course of time, we learned how to do some stuff with them, but the name stuck. Imaginary numbers, complex numbers, they are all the same thing. But that imaginary idea and the I that they're using, that all came from them just not knowing what to do with it, but knowing it should be there. So complex numbers really is a lot like what we were just doing. If we're going to simplify the square root of -24, so we're just going to kind of bridge in between complex numbers and what we were just doing. The negative, that gets the I part. So the negative gets the I part. But then we break down the 24 just like we did in the last section. We do the factor tree thing. 24 is 8 times 3, 4 times 2, 2 and 2. There's a pair of 2s. So that's 2 on the outside and a 6 on the inside. The only difference is it has the I out there with it because it was negative. Anytime you have a negative under a square root, you know an I is going to come out automatically. No real calculation involved. It is automatically going to have an I. 3 times that 2. That's where those came from. If nothing else will come out. So if I go to break down the 35, I know that's 7 times 5, and those are both prime. There's not any pairs here, right? So nothing comes out except for what? It's got a negative inside of there, right? So that's I radical 35. because we didn't have any pairs, we can't change this number in here. So, but the I can pull the negative out. That's what happens there. It's just an I comes out of that. If we had the square root of negative 168. Big number. Maybe it's got some stuff in it. We'll break down to 168. It's even, I know that. So 2 goes into it 84 times. And 84, what do I know about it? It's even too, right? So 2 goes into it 42 times. Now I'm getting down to some smaller numbers, and maybe I know a little bit more about. What do we know about 42? 7 times 6. And 6 is 3 times 2. Hey, got a pair of 2s right there. But these 3 don't have anything to partner with there. So only just a 2. And what else comes out? An I, because it was negative, right? And then 3 times 2, 2 times 3 times 7 is going to be the 42 left in there. So simplifying square roots. Now, when you're dealing with multiplying square roots, you've got to be a little more careful when there are negatives on the inside. Okay? When there weren't negatives, the rule was just to multiply inside times inside, outside times outside, and then simplify last. When there are negatives on the inside, we've got to get the negatives out of there first before we do anything else. So what I do is I just pull out the I, and then do the math from there. Okay, and this is where that chart that we wrote at the beginning of the lesson of this section comes back. Okay, because when I multiply I times I, it's just like if I multiplied x times x. X times x is x squared. I times I will be I squared. And then 7 times 8 is going to be 56. And I'm going to break down the 56. Got a pair of 2's. So that's 2i squared, radical 14. What do I know about I squared? It's negative 1. So that's going to be 2 times negative 1 square root of 14, which is negative 2 square root of 14. Negatives in there, you've got to take care of the i's first, then work the numbers. We had negative 12 times the square root of 15. Square root of negative 12 times the square root of negative or positive 15. Again, I would pull the I out at the beginning because there was a negative involved, and then do the math. So that's going to be I radical, whatever 12 times 15 is. 12 times 15. 180. Pair of 3's, pair of 2's, 5 left over. That's going to be 6i radical 5. The negatives, throw in that. All right. Now, I want to show you some operations with just complex numbers. So we're going to add, subtract, multiply, and divide complex numbers. I'm going to show you how to do this by hand, and then I'll also show you how your graphing calculator can do the adding, subtracting, and multiplying and dividing of complex numbers. So we're going to add, subtract, multiply, and divide complex numbers. And this is that A plus BI stuff. A plus BI. That's a complex number. That's the way we want our answers to end up looking like that. The real number part in the front, the imaginary part in the back. Now, with your graphing calculator, before we dive off into this, let's get everybody set to the right mode to be able to do this. So if you got your graphing calculator, get that thing out, get it turned on, wind it up, whatever you got to do. Okay. Hit mode, which is the right beside the blue button, and you should have a bunch of menu stuff come up. Turn it on, hit mode, and then look for a line that says real A plus BI, and then this RE raised to theta I. That number. Okay, you want to have A plus BI. Okay, if you're running the 2.55 or later edition of the operating system, or if you've got a color one, it should have that. So we want A plus BI selected. Make sure that line is selected. Is everybody finding that? This will allow your calculator to do some work with complex numbers for you. Okay. All right. So second mode to get out of that, or you can turn it off and turn it back on. It'll get you out of it too. All right. Now let's look at some examples here. I don't know what were they. F. Example F. Two complex numbers, 3 plus 5i plus 6 minus 2i. That's two complex numbers. We're going to add them together with plus sign in the middle. Okay? That looks a whole lot like adding an expression that has like terms, doesn't it? What would be the like terms? 5i and negative 2i, 3 and 6 would also be like terms, right? Because they're just regular numbers. So I could do this by hand. I could say 3 plus 6 is 9. 5i minus 2i would be plus 3i. That's correct. That's the right way to do that. Okay? Your calculator can do it as well. I usually don't do addition and subtraction in the calculator just because it takes me longer to type it in than it would have done to do the problem. But I want to show you that it will do it. Okay? So we were going to do 3, so parentheses, 3 plus 5, and then to get the I, you hit second decimal point. Second decimal point gets the I in the problem. And then I'm going to close my parentheses, plus parentheses 6 minus 2, second decimal point to get the I. Close the parentheses, just hit enter. Bada bing. Same answer we got to do. Again, I usually don't do addition and subtraction because it's too easy to do just regular. But it will manipulate that complex number for you. That's kind of nice. Did anybody not get that to work? You're just giving your error. Okay, let's see if we can use just small thing. Okay, we were doing this in my classes at school the other day. Same issues. Okay. All right. Let's do a subtraction problem. 3 plus 5i minus 6 minus 2i. So if I'm subtracting two complex numbers, 3 minus 6, it's negative 3. 5i minus negative 2i would be 5i plus 2i, which would be plus 7i. If I'm not too confident in myself, maybe I just want to check it, and maybe I just like how my calculator works. I'm going to do 3 plus 5i, close parentheses, minus, parentheses, 6 minus 2i. Crank that out. Wow. Does it for me. Same answer. Okay. So addition, subtraction, again, I probably wouldn't do it in the calculator, but you can. Okay. Let's do some multiplication. H. 3 plus 5i times 6 minus 2i. This looks incredibly similar to what we did at the beginning of the class. We're multiplying out those binomials. We did like FOIL method. This is exactly that. No different. Only difference is the I has some meaning behind it besides an X. So if we did distributive property, 3 times 6 is 18. 3 times negative 2i would be negative 6i. 5i times 6 would be plus 30i. 5i times negative 2i would be negative 10i squared. The difference is I've got to simplify this, and I know that I squared turns into what? Negative 1. So I know that this is actually not minus 10i, but minus 10 times negative 1, which would be 18 plus 10, right? Because that's a positive 10 now. So it'd be 28 plus, and then negative 6i and positive 30i would be 24i. Now, that's a lot of steps. It's more than the addition and subtraction is for sure. If I put this into my calculator, it's going to crank it out for me. No steps in between. Parentheses 3 plus 5i. Parentheses 6 minus 2i. Enter. Does it for me. And it simplifies out the I squared and all that stuff for me. Absolutely legal and absolutely wonderful for you to use. Okay. So the multiplication, you can do it by hand, you can do it with the calculator. It makes me no difference. Now, when I come to the division, these are the ones that I usually do with the calculator, because the division, I'm going to show you how to do it by hand, just so you appreciate the calculator. Quite a lot on this. All right, so division of two complex numbers. 3 plus 5i over 6 minus 2i. Okay, you're dividing those same two complex numbers. In order to do this by hand, you have to multiply by what's called a conjugate. And the conjugate changes the sign in the middle. And it would be 6 plus 2i. And you multiply top and bottom by that. And so you're multiplying all this stuff out. So on the top, it'd be 18 plus 6i plus 30i plus 10i squared. On the bottom, you got 36 plus 12i minus 12i minus 4i squared. So I'm just doing distributive property to multiply that across. Then I'm going to simplify. So that's a whole nother step. So I've got to know, okay, well, this thing turns into negative 10. This thing turns into positive 4. And these cancel out. So the top part's going to be 18 minus 10 is 8 plus 36i. On the bottom, I got 36 plus 4. So that'd be 8 plus 36i over 40. And then what do I know about each one of these? They're all divisible by what? 2 goes into them, but 4 is bigger and it goes into all of them too. I'm going to divide everybody by 4. So it'd be 2 plus 9i over 10. And then I've got to split that apart into 2 over 10 plus 9 over 10i to get it in complex form. And 2 over 10 actually reduces to 1/5. Finally, I'm done. 1, 2, 3, 4, 5, 6, 7 steps to get that done. So division with complex numbers, quite the difficult task, unless you got a graphing calculator. So we need to put the top part in parentheses, 3 plus 5i. Close those parentheses, put a division symbol, and then do the bottom part, 6 minus 2i. Do not use the fraction button part of the calculator like you did alpha F1 to get the fraction thing. He can't figure that out. He can't do that. I didn't know that until just a few days ago. We were doing it in my 2 class, and they found out that it won't do it that way. Now, that doesn't look like the answer that I got. It's decimals. I want fractions. How do I change it into fractions? Math, enter. Bang. 2 steps versus 7 steps. Much easier. Okay. And I absolutely encourage you to do the complex numbers with your calculator. Absolutely encourage that. No sense in missing any out of pride. If you want to do them by hand while you're practicing, that's fine. But don't miss them because you need that. All right. So problems, suggestions for the sections. The first section, 1 through 37, odd. The second section, I'll write the numbers in just a second, 45 through 85, odd. And then 1 through 45, 51 through, and then this is 1-3, this is R.7, this was R.4, and this was R.3. Those are your suggested problems. Put out quizzes for all 4 of those sections this week. We will come in next week. We will have labs at the beginning, and then an assessment over these 4 sections. Okay? That's how class will go next week, and then we'll pick up from there. That is the plan of attack. If that changes, I'll send you an email and let you know that stuff. So email me if you got questions. Let me know what's going on, and I will see you next week.